The earliest computing device developed by man was back in 1100 BC. It was the humble abacus. The purpose of the abacus was to perform rudimentary mathematical operations. It had several rods and weights attached to each rod. This allowed the representation of numbers that could be manipulated to perform addition, subtraction, multiplication, and division. This allowed for basic computation and record keeping. On screen is a version of the abacus used in ancient Rome. Fast forward a millennium, calculators had been invented and a large number of variations of basic computing machines had been developed by the 1700s. In 1800, Charles Babbage introduced an automatic mechanical calculator designed to tabulate polynomial functions. This would prove to be the foundation of modern computers. By the year 1880, the US population had grown so large that it would take more than 7 years to tabulate the US Census results. This was one of the catalytic reasons that led to the development of computing systems and memories. In 1890, Herman Hollerith, an American businessman, inventor, and statistician, developed an electromechanical tabulating machine using the concepts of jacquard machines by using punched cards to assist in summarizing information. The idea was to eventually use this for accounting. This invention was used to calculate the 1880 census, accomplishing the task in just 3 years and saving the government $5 million. He later established the company that would ultimately become IBM. In 1936, the first theoretical concept of a modern computing device was formed by Alan Turing. This was known as the Turing machine. The idea was that a piece of infinite tape had ones and zeros on them, which would act as the instruction set, and then the final output of the computation after processing it. This would prove to be the foundation of computer science and AI. The Turing machine involves a piece of tape. This is the instruction set. The machine or the computer would read each and every bit in the tape and perform an action based on its state, the state changing with the read bit. The action could also change the bit stored on the tape. Finally, the computer would reach a halting state. The modified tape would be the output of this computation. Alan Turing, as we discussed, developed the Turing machine in 1936. He was a British mathematician and logician. He made major contributions to mathematics, computer analysis, logic, philosophy, and mathematical biology. The Turing machine and his further ideas led to the beginning of modern computer science and artificial intelligence. He theorized that the cortex at birth is an unorganized machine that through training becomes organized into a universal machine or something like it. Let us take a look into the imitation game. This game involves a male and a female participant as the communicators and a participant of any gender as the interrogator. Let's say the communicators are Ayushi and Omkar, and the interrogator is a mixed group, Ojaswa, Nikita, and Richanshu. The communicators are separated from the interrogators and can only communicate with typed notes. During the game, the interrogator asks a series of questions to both the communicators. The objective of the interrogator is to find which of the two communicators is male and which is female. The objective of one of the communicators is to deceive the interrogator, while the objective of the other is to lead the interrogator towards the correct answer. In this scenario, Omkar will ensure that all messages coming from him will make it seem that they are coming from Ayushi, while Messages from Ayushi will try to enforce the idea that her set of messages is from herself. The game tests the ability of player 1, here Omkar, to imitate the behavior of player 2, that is Ayushi. Alan Turing used the same concept but with a machine. If we replace player 1 with a machine, that is an artificial intelligence, the game objective could be repurposed to find whether the AI can successfully imitate a human being. This led him to develop the Turing test in 1950 that would attempt to find out whether an AI could think like humans did. The standard Turing test consisted of 3 physically separated stations. One was controlled by a computer, while the other 2 were managed by humans. In the test, one of the humans was assigned the role of the inquisitor, while the other human and the computer acted as the respondents. The inquisitor asks a question on a specific topic using a specified format and context. The computer and the human respondent both give their responses to the inquisitor. After a decided amount of back and forth, the inquisitor was asked to decide on which respondent was a human and which was a computer. The test is repeated multiple times, and if the inquisitor correctly selected the human response in half or less of the total number of tests, then the computer was considered of human-like intelligence. This is because, essentially, the inquisitor selected the AI's response as the more human one as compared to an actual human response. As we can observe, the Turing test has many variables to support its result. The 3-player situation is not clearly specified. It has many versions. One version can be when the inquisitor has not been informed that one of the participants is a machine. Will the results be the same as when the inquisitor had been informed, or will the result be different? Another version can be when player B knows that player A is a machine. Will the result be the same as when player B does not know about player A? These versions will give Inquisitor different responses from players and can be used to validate the AI's performance further. Additionally, the limitations imposed on the test environment can greatly affect the performance of the AI decision. For example, every computer system or program is designed to work on a specific set of instructions. That is, every AI has a specific context that is provided to it to allow it to understand and process the question. If a question provided to the AI is outside the correct context, then the processing may be flawed and it may give an undesirable output. Hence, for the Turing test to work, it is important to limit the variations and questions to the expected domain for the AI. The Turing test is successful primarily due to its ability to test non-specific terms such as intelligence in a simple and accessible manner while still providing a specific answer. Moreover, the test is designed to eliminate the inability of the machine to appear as a human and the human's inability to function as a machine by focusing only on matters of the mind. Turing wrote that he did not wish to penalize the machine for its inability to shine in beauty competitions, nor to penalize a man for losing a race against an airplane. The test is also able to explore a broad variety of topics and perform a large variety of tasks through the nature of the question and answer process, proving to be another strength. The machine must be able to communicate successfully in a spoken or written language, retain the information that it hears, utilize the stored information to form new conclusions and ideas, and detect speech patterns and adapt to new situations. These are computationally complex paradigms. Some of the steps and processes developed to achieve this are as being shown on screen. These requirements are the most important focuses in furthering AI and a great test to validate whether the computer can think in the same way as us. The Turing test acts as an all-inclusive test of these. Another strength of the Turing test is its ability to eliminate hindrances derived from an individual's unique and specialized knowledge, since it is based off of general interaction. Finally, it is easily adaptable. Its simple design allows for many alternative games and experiments to be derived from it, such as the inclusion of more players or changing the rules of awareness that are placed on each individual. A decade after the Turing test was proposed, Joseph Weizenbaum of MIT developed a program known as ELIZA. Weizenbaum wasn't attempting to create a program that would pass the Turing test. Far from it. ELIZA was the first attempt to create a natural language processing computer program from 1964 to 1966 at the MIT Artificial Intelligence Laboratory. ELIZA's creator, Weizenbaum, regarded the program as a method to show the superficiality of communication between a person and a machine. ELIZA worked by using a pattern matching and substitution methodology that gave users an illusion of understanding on the part of the program but had no built-in framework for contextualizing events. The program would examine users' typed comments and look for keywords. In the event that a keyword is found, the program would supply a sentence that included a transformed comment submitted by the user. In the event no keyword was found, the program would supply a generic answer or revert repeating an earlier comment. The program actually had two parts, a general purpose engine and a script. The program became best known via a doctor script that simulated a Rogerian psychologist. The script Doctor, simulated by psychotherapist Dr. Weizenbaum, made ELIZA into a therapist because therapists often ask open-ended questions. Therapists aren't supposed to give you advice, and they are not supposed to tell you what to do. They are supposed to ask questions and trick you into saying more on the grounds that this will be revelatory and will help you figure out things yourself and will aid your mental health. This made things easy programming-wise. All ELIZA had to do was listen to you, what you said, that is, parse your sentence in a very basic way and then ask you a question in some way related to the sentence you had typed. So, if you mentioned your sister, say ELIZA would reply by saying, "Tell me more about your sister." In experiments during the 1960s, people were fooled by ELIZA. They were told that a real-life therapist was talking to them from a second computer, and they believed it. As such, ELIZA was one of the first chatbots, but was also regarded as one of the first programs capable of passing the Turing test. Many academicians believed that the program would be able to positively influence the lives of many people, particularly those suffering from psychological issues, and that it could aid doctors working on such patients' treatment. Though ELIZA was capable of engaging in discourse, ELIZA could not converse with true understanding. However, many early users were convinced of ELIZA's intelligence and understanding. The following is a conversation between ELIZA and a person. I feel happy to be writing right now, to be typing this as we speak. Lately, I've had the writer's block. You say you mean? That's what I said. Can you elaborate on that? I only really feel happy when I'm writing. How long have you been writing? Always, but I've been writing seriously since I was 18. What does that suggest to you? I don't think it's enough to only be happy when you write. Does that trouble you? You can't write all the time, and then there's the real world, and you still have to deal with real people. Weizenbaum was shocked by the experience of realizing ELIZA, also known as Doctor, to the non-technical staff at the MIT AI lab. Secretaries and non-technical administrative staff thought the machine was a real therapist and spent hours revealing their personal problems to the program. When Weizenbaum informed his secretary that he, of course, had access to the logs of all the conversations, she reacted with outrage at this invasion of her privacy. Weizenbaum saw this and other similar incidents to find that such a simple program could so easily deceive a naive user into revealing personal information. Weizenbaum perceived this own program as a threat, and his first reaction was to shut down the early ELIZA program. He also wrote a book about the whole experience, eventually published in 1972 as Computer Power and Human Reason. Eliza could pass the Turing test simply by manipulating symbols of which it had no understanding. Without understanding, it could not be described as thinking in the same sense people are. The Turing test is concerned strictly with how the subject acts, that is, the external behavior of the machine. In this regard, it takes a behaviorist or a functionalist approach to the study of the mind. The example of Eliza suggests that a machine passing the test may be able to simulate human conversational behavior by following a simple list of mechanical rules without thinking or having a mind at all. Most contemporary researchers did not need much convincing that Eliza was at best a gimmick, at worst a hoax, and in any case not a serious artificial intelligence project. The Artificial Linguistic Internet Computer Entity, also known as Alice or AliceBot, was a chatbot developed in 1995. It was inspired by Eliza and has won the Loebner Prize 3 times. The Loebner competition is a competition between talking computers. Each program goes through rounds of Turing tests, and the best performing program is judged the winner of the Loebner Prize. The better-known version of the program was written in Java beginning in 1998 and used an XML schema called AIML, that is, Artificial Intelligence Markup Language, for specifying the heuristic conversation rules. This was one of the first chatbots to use natural language processing to try to understand conversations. However, the program did not manage to pass the Turing test as the mechanisms and logic of its conversations were apparent very easily. Mitsuku, developed by Steve Warswick since 2005, is a chatbot from Leeds, England. It has been designed using all of the AIML files of Alice and is considered its spiritual successor. The program uses modern natural language processing techniques and has the ability to understand objects and object properties. For example, if someone asks, "Can you eat a bridge?" the program's advanced natural language processing allows it to identify the roles of eat and bridge in the sentence, look up the edible property of a bridge, and respond with no. It has been awarded the Loebner Prize 5 times due to its incredible performance and understanding capacity. However, like Alice, it too has not been able to pass the Turing test. Till the 21st century, the most advanced chatbots had the capacity to parse sentences and gain limited semantic information about the nature of the sentence and respond with a sentence that could be construed for true intelligent thought. While they did not directly lead to thinking machines, they helped develop many of the technologies in the fields of AI and machine learning, the foundation of which was the perceptron. The working unit inside the human brain is called the neuron. It is a specially designed cell to transmit messages to each cell. Advancements in neuroscience have revealed that it is these neurons that facilitate thoughts and emotions. In a neuron, the part called the dendrite receives electrical signals or pulses from other neurons. These pulses pass through the axons and are of varying strengths and modulated by the axons in different amounts, stimulating thought. It is arguable that in order to recreate human thought, we should recreate the human neuron. The first artificial neuron was the threshold linear unit, that is TLR, proposed by Warren McCulloch and Walter Pitts back in 1943. 1.5 decades later, in 1958, Frank Rosenblatt from the Cornell Aeronautical Laboratory invented the perceptron, the foundational step in modern machine learning. A single neuron was incapable of recognizing patterns and led to the invention of feed-forward networks, also known as multi-layer perceptrons. The 1960s saw the invention of backpropagation, a revolutionary algorithm that could train multi-layer perceptrons. 1960s to 1970s were the golden age for artificial intelligence and progress towards thinking machines, as these inventions led to a great deal of research. However, progress towards thinking machines slowed down until the end of the last century, when more powerful processing units and chips were available to the researcher who did not have access to supercomputers. Eugene Guzman was a chatbot developed in St. Petersburg, Russia by a group of 3 programmers. On June 7, 2014, at a contest marking the 60th anniversary of Turing's death, 33% of the event's judges thought that Guzman was human. Alan Turing had made a prediction in 1950 paper Computing Machinery and Intelligence that by the year 2000, machines would be capable of fooling 30% of human judges after 5 minutes of questioning. The event's organizer, Kevin Warwick, considered it to have passed Turing's test as a result. So, does it mean computers that think like humans are already here? Not necessarily. Turing test's ability to test the thinking capacity has been rightly criticized. Programs such as ELIZA have repeatedly fooled unsuspecting people into believing that they are communicating with human beings. But this was because it simply regurgitated sentences using predefined logic. To successfully appear human, there was no need for the machine to have any intelligence whatsoever. While a computer truly capable of human thought would perform as well as any human in the Turing test, the opposite is not true. Just because a program beats the imitation game does not mean it has the ability of human thought. None of the chatbots to date displayed true thought. So, where does that put us en route to thinking machines today? Today, we live in the era of machine learning and AI. We have the computing power to create large, deep neural networks which we could never imagine before, allowing programs to blur the lines between computer and human insight. With the availability of the internet and social media, there is terabytes of usable data of conversations to train these algorithms on. Tech giants such as Google, IBM, and many more are constantly investing millions of dollars into research and development of more capable AI, a sizable sector of which is AI that can understand, react, and even conjure human thoughts. We are not there yet. As we concluded, the best conversational algorithms to date can at best imitate language, not think human thoughts. So, can we or can we not expect computers to think in the sense that humans do? The human brain has close to 80 billion neurons. The largest artificial neural networks to date have a size of close to 20 million neurons. While this is not even close, it is leaps and bounds ahead of our computational capability 70 years ago when artificial intelligence was still in its infancy. Back in the 50s, the fastest supercomputer that was worth $9 million could compute close to 500,000 floating point calculations per second. Today, a GTX 1080 and $800 GPU can compute 8.2 trillion floating point calculations per second. The second biggest roadblock to the computation is the space requirement. Back in 1950s, a state-of-art $50,000 hard drive that weighed a ton and was the size of 2 refrigerators could store 5 MB of data. Today, a $50 hard drive available at any regular electronics store could store a million megabytes, that is 1 terabyte of data. The advent of the internet has given rise to new technologies. Notably, cloud technologies now enable us to execute a program in parallel over an array of computers, giving a gigantic leap to computational capacity. High-performance cloud storage solutions could solve the memory requirements of more advanced AIs of the future. With artificial intelligence, machine learning, and natural language processing being one of the fastest growing sectors in tech today, tens of billions of dollars are being invested in the research and development in the field as furthermore advanced intelligences are being made every day. Quantum computation has already been achieved. Though still in its infancy, it is under constant development. In the next 50 or so years, we could see quantum computers revolutionize the field of machine intelligence and learning. The already apparent explosion of data available for the research and development of these computers is only expected to increase in the coming decades. Along with this trend, with the coming years, we will have exponentially higher computational capabilities that will ultimately lead to more breakthroughs in the field of computer science that will put us further in the road towards computers that think. We are still a long way from reaching computers that think like we do. But yes, in the next 50 to 100 years, we can expect a number of breakthroughs in AI to facilitate the development of the first computer that can really think like humans.